Hey, another problem today. So this one also a 1900. So let's begin with examples. So in the first example, we are going to give a array with 5 items, and we are going to do 5 operations as well. So first, this is the initial array. So um, in our set, we are going to have 1, 2, 3, 4, 5 numbers. And then if the in the operation array, if the number is less than 0, it means we want to remove the if it is -1, we want to remove the first number in our current array. So in this case, we are going to remove 1 and another -1 operation. So we are going to remove the first number in our current array, which is 2. And so on and so forth. Eventually, we are going to remove all of the 5 numbers, and we output because the array is empty now, so we output 0. For the second case, um, the initial array is 1, 2, 3, 4, 5, and we want to remove the 5th number first. So this one is removed, and then remove the first number. This one removed. Then remove the third number, 1, 2, 3, and remove the first number, 2. So only 3 is remain in the array. So we output 3. And for the last test case, these two numbers are bigger than 0. That means this operation is to add a new number into the array, which is 5 and 6, right? Eventually, you want to output just one number. It can be any of the numbers in the final array, right? So in this case, there is only one number, so we output 3. In this case, we have a lot of numbers. We can output any of them. So in this case, we output 6. So how to resolve this problem? So this problem has very strict memory limit. So we want to use a binary search to resolve this problem, because if we use binary search, we only need ON memory memory size, right? So how do we do it? So for this operation kind of problems, keep in mind that is you can do the calculation offline. That means you can use you don't have to calculate the final answer each time you made a operation. You can calculate the final result by using all of the operations, right? So in this case, we just need to find one of the numbers in the final array. So to do that, we might want to find a specific number in the final array. So in our strategy, we are going to find the leftmost number in the final array. How can we do that? So the leftmost number in the final array is also the biggest number that all of the numbers smaller than it are removed, right? So we are going to find the biggest number, that all the numbers that are smaller than it are removed. So we can use binary search. We can just um, search from 1 to maximal uh, to see if the current number is the bigger is the all the numbers smaller than the current number are removed in the final queue, in the final array. So how can we test that? So we can iterate over all the first array and then iterate through all the operations and find out if the current number or if to find out if all of the smaller numbers are removed in the final array. So how can we do that? So we are going to iterate all the positive numbers in these two arrays. If we find a number that is smaller than mid, we increase the counter, right? If we want to insert a number that is smaller than current number, we increase the counter so that we know how many numbers are smaller than current number. So if the number is eventually 0, that means it fits this condition, right? And if we find that is how we deal with the positive numbers, right? And if we find a negative number and the absolute value of this negative number is smaller than current count, right? Then count is decreased by 1, right? Because the ranking of the current number is count now, and if we want to remove a number that which ranking is less than the counter, that means the current rank of the number is decreased by 1, right? And eventually we check the count here. If it is equal to 0, that means all of the numbers that are smaller than this number are removed from the final queue, right? If it is bigger than 0, that means not all of them are removed. So we want to run the binary search again. So the time complexity of this solution is log n, right? Binary search is log n multiplied by n, which is the time complexity of the checking strategy, right? So it can pass all the examples. I mean, pass all the test cases. So let's look at the code here. First, we read all the initial numbers, and then we read all the operations, and then we run the binary search. And this is where we run the binary search. And here is we iterate over all the initial array, and if it is less than mid, mid is our current number, right? Our target. We increase the counter, and then we iterate over all the operations. If the operation is positive, we check if we want to increase the counter. And if it is negative, we check if we want to decrease the counter, right? And then if the counter equals to 0, we here is how we change the range so that we can iteratively do the binary search, right? Eventually, we want to output the answer. So that's it. Hope it helps. See you next time.